Hello everyone, this is Group 28, and our project is to reproducing the paper Semi-Supervised Classification with Graph Convolutional Networks. The motivation behind the paper is to address the problem of semi-supervised learning on graphs. In many real-world scenarios, we have access to a large amount of unlabeled data, but obtaining labeled data can be expensive or time-consuming. Graphs are a common way to represent structured data, such as social networks, citation networks, and molecular structures. Graph convolutional networks, GCNs, were developed to address this problem by operating directly on the graph structure. However, existing GCN models were mostly designed for node-level tasks and did not fully exploit the graph structure to improve the performance of the model. The authors of the paper propose a new type of convolutional operation that operates directly on the graph structure, allowing the model to better learn from the graph structure and the node features. The GCN model proposed by the author is a two-layer neural network of graph convolutional layers. The first layer is a graph convolutional layer with 16 hidden units, followed by a ReLU activation function. And the second layer is another graph convolutional layer, which serves as an output layer and has as many output units as the number of classes in the classification problem. In the graph convolutional layer, the features of each node are updated by using an aggregation of information from neighboring nodes to capture local relationships and structures present in the graph structure.
Next, we'll discuss our reproduction attempts of the graph convolutional networks paper, along with ablation experiments we performed and our future plans for this area of research. First, we cloned the original repository to obtain the code from the authors. Then, we adapted the code to run on TensorFlow 2.0, which involved modifying certain functions and importing libraries to add compatibility for certain older pieces of code. Our reproduction results using the author's original configuration showed the following: improved speed compared to the original paper. This is likely due to advancements in hardware now that we're in 2023. The accuracy levels were similar, which confirms the original findings across the three datasets of citation network data. In terms of ablation experiments, we conducted ablation experiments to explore potential improvements to the GCN model. We experimented with different activation functions, optimizers, and the number of layers. In terms of activation functions, we used an additional 4 activation functions on top of the ReLU. There was no significant difference in performance, with the exception of the sigmoid activation function, which significantly underperformed. In terms of optimizers, we used an additional 3 optimizers. We found that by tuning learning rates, we could achieve similar or slightly better results than the original model across all of the datasets for any of the optimizers. In terms of number of layers, we both attempted to add a layer and remove a layer. We found that doing so modified the results, but we need to investigate further to see exactly what might be happening when we modify the number of layers and why the results are changing in the direction. In terms of future steps, we want to expand the types of datasets used in experiments beyond just citation networks to further generalize the methodology and see how it applies across other areas in graph structures. We want to perform more extensive hyperparameter tuning, such as learning rate, citation functions, and optimizers. And we believe something like a grid search could definitely help find ideal combinations for different datasets. In summary, our reproduction of the GCN paper confirmed the original findings and allowed us to explore potential improvements to the model. Our ablation experiments show how different aspects of the GCN model may influence performance, which can be the subject of further studies and experiments. Thank you.